My first introduction to electronics devices was when I was a kid, when I saw my grandma using a handheld glucose monitor. During my master thesis project, I worked on sensors which can detect serotonin in buffer solutions, and that reminded me of the glucose device my grandma used to hold. That was a moment when I decided a PhD in engineering is what I would like to do for the next 4 years. I'm Seerat, a PhD researcher at UCL's Department of Electronics and Electrical Engineering. Cardiac amyloidosis accounts for 15% of the total heart failure cases worldwide. There is this one protein called transthyretin which misfolds and dances into all these weird configurations which later deposit as a clumpy fold called amyloid in the heart. The real issue lies with the physical and chemical nature of these misfolding dancing species, which make them really difficult to detect. What we are interested in here are non-invasive pre-screening tools which can help us monitor this disease at an early stage and help us better regulate the disease progression. Here I'm developing low-cost devices. This device is similar to a smart fish net, which when thrown in a crowded pond can specifically recognize this one fish. So here the pond is human blood or plasma samples, and the fish is transthyretin, which is the precursor protein for this fatal condition. To catch it, I'm using antibodies, which is similar to using a fishing bait, which can specifically recognize these protein molecules. It is then mobilized on a sensor surface, which can be thought of as a fishing net on which this special bait is fixated. When deployed in patient samples, this interaction between the protein and the antibody results in a change in something called impedance. And that change in impedance tells us the levels of this protein present in human samples. One of the things about these devices is that we wanted to make them low cost and accessible to resource-limited settings wherein this condition is supposed to be endemic. When it comes to fabricating these electrodes, I'm collaborating with UCL's Institute for Materials Discovery. The gold atoms are spotted on a substrate which can either range from a baking paper to a ceramic. The thickness of these electrodes could range from 5 nanometers to as thin as 100 nanometers. Apart from this, in order to realize how this device can better help us pre-screen patients for this fatal condition, I have collaborated with clinicians and researchers from Royal Free Medical Hospital in Center for Amyloidosis who specialize in diagnosis and treatment of these patients. What I love about what I'm doing is the very opportunity to work at the intersection of biology, chemistry, and electronics, and seeing that this device can actually impact patient lives. In future, I can see myself working at research, innovation, and accessibility, making devices that people are empowered to use on their own, and it is not limited by the environment they are surrounded by, or the income they earn, or the country they are based at, or what's their nationality. STEM can be really overwhelming just because there's a need to be novel, there's a need to publish. Don't let that shatter your hope or diminish your light. There is where the real growth lies.